How's it going, ladies and gentlemen? Mr. Donnie here once again, this time taking a look at 25.3 stuff, alkanes. So our objectives are to describe the properties of alkanes, including common reactions, their structures, and isomers, as well as physical properties. All right, so writing formulas for alkanes. So we have the Lewis structure over here with lines for single bonds and shared electrons. You guys are familiar with this. So we also want to be able to draw these in the condensed structural formula. So basically, the condensed structural formula is going to condense this Lewis structure, but still show you the structure of it. So basically, like, you could condense this all the way down to C4H10, but then you have no idea how those connected together. You don't know what's going on. So this is not very helpful. What we want to try and do is use a condensed structural formula, which is going to show the structure still. So basically, all you do is you look at one carbon at a time. So I got carbon, and off of that, I got 3 hydrogens. Right, so I've done this part. Now I look at the next carbon. I got a carbon with 2 hydrogens on it. Check. Check. And then I go again. I got another carbon with 2 hydrogens on it. Check. And then I have a carbon with 3 hydrogens on it. Check. So that is the condensed structural formula. You see there's a carbon with 3 H's, carbon with 2 H's, carbon with 2 H's, carbon with 3 H's. There's also a shorthand, which is just this. If you want to know how to do that, I got another video just for that, the crazy shorthand. That's so awesome. Anyway, so structures of alkanes. You got to realize that these carbons are sp3 hybridized, which means that they're going to have a tetrahedral shape. Okay? And you can have spinning around the sigma bond. So anytime you have a single bond, those things are able to rotate and spin around that bond relatively easily. Pi bonds, which we'll get into when we do alkenes and alkynes and stuff, the double and the triple bonds, they lock the arrangement into place. You can't spin around that bond. Show you what I'm talking about, okay? Long chains are going to twist and move constantly because if you got long chains all single bonded, each one of those bonds can spin around itself. So it's like a shaking chain. So what shape is it going to take? Well, it's always changing shape because it's like a chain that's being rattled around. It can change its shape. So here's a demonstration, right? I got a simple carbon atom right here, and I'm spinning it along this sigma bond right there. So you can see it can spin, right? I'll show you one more time. It's spinning, it's spinning, it's spinning around that sigma bond. Now, if we had an entire molecule, it's going to be able to do the same thing. So watch what happens. So, I got to press play. So here's butane, and each of those sigma bonds, the molecule can spin around. So it can spin around like this, and the shape stays kind of the same. But hey, look what happens when I spin it this way. Now I got like a different overall shape, but it's still the same molecule. I didn't change any of the bonding. I just changed its orientation in three-dimensional space because it's able to spin, right? So if I pause it right there, I got this U shape, when before I had like kind of this zigzag shape. It's still the same molecule, but it just spun. So that's the only difference. All right, so structural isomers. Straight chain hydrocarbons. They make straight chains of carbon, right? Pretty straightforward. If you see somebody talking about straight chain hydrocarbons, it's just a straight chain, not blowing your mind. What you could also have is branched chain hydrocarbons. So when there are 4 or more carbons, you can make branches instead of everything being in a straight line. A structural isomer is a compound with the same molecular formula, but with different bonding arrangements. So branched chain hydrocarbons are, isomers of straight chain hydrocarbons. So I'll show you what I'm talking about. So C4H10. I can have a straight line of carbons in a chain, and then each one of these lines would have a hydrogen on it, and that is my C4H10. I can have an isomer where I kind of take one of these and I pop it off and I put it on a central carbon. So I end up with a carbon, 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 and instead of having another carbon here, I took that carbon and I put it on the middle carbon. So now I have a branched chain hydrocarbon that is a structural isomer, because if I take a look, well, the formula for this is still going to be C4H10, and the formula for this one is still C4H10. So they have the same formula, but different structure. So they're structural isomers, right? Iso means the same, mer means parts. So they're made of the same parts, but they're put together differently. So same thing for pentane. Straightforward, straight chain pentane. I have a chain of 5 carbons. What can happen is I can take one of those carbons and pop it off, and I can put it on a central one. So I can go, all right, I can have boom, boom, a chain that's 4 carbons long, and then put the 5th carbon on one of those central ones, and then complete all those octets. And now I have a different structure, right? If I were to do the shorthand, it looks like this. Boop. Shorthand for this one looks like this. And I can even do it one more time, where I end up with a carbon chain of 3 long, and off of that middle carbon, I got 2 more carbons. And the shorthand for this would just pretty much be that, right? Or more likely, you probably see it like bent like this, and then boop, boop. These are all still C5H12. They're all structural isomers made of the same parts, just connected differently. So question, are these 2 things isomers? Well, let's see. I have 5 carbons, and I have 12 hydrogens, and then I count here C5H12, still awesome, right? There's a hydrogen hiding behind here that you can't really see. So they have the same formula. So are they isomers? Well, they look different, right? No, they are not isomers. Why? Because all this is twisted. So it took this, and I twisted this carbon, I twisted a little bit to get it to bend and look different. Is any of the bonding differently? No. I can do it out this way. C3, CH3, CH2, CH2. Again, there's a hydrogen behind there that you can't see. And then CH2, CH3. And this is the same for both of them. There's no difference in structure. Okay? So, how do we name these? That's a great question, and that is a video all in of itself. So look for another one on how to name these things. Cool. So we have these other things called cycloalkanes, and if you had to guess, you could probably guess it has something to do with making a circle, right? Cycloalkanes, making a circle. So cyclo, rings are made from carbon. So if I take a look at this one right here, I made a ring. I made a ring with this one over here. These are rings made from carbons, and alkanes is telling you that they're all single bond. So as the circle gets smaller, it puts more strain on the bonds, and the molecule tends to be more reactive. So think about the deviation from the ideal bond angle. Carbon wants to have tetrahedral shape when it's sp3 hybridized, which gives it a bond angle of 109.5 degrees. And if I'm taking a look at this, I'm making a triangle, an equilateral triangle, where all of those angles are going to be 60 degrees. So there's huge deviation for the little guy, the cyclopropane, the triangle, from the ideal bond angle, which makes this a very reactive molecule, whereas this one, the bond angles are closer to 109.5, so it's going to be less strained, and this is, I think, let me count, 1, 2, 3, 4, 5, 6, cyclohexane, relatively stable. Okay? So yeah, sometimes they behave as unsaturated hydrocarbons do. It's the same general formula as alkenes. That's why you get some of those similarities. Right? So if I take a look at here, I have 3 carbons and I have 2, 4, 6 hydrogens. So C3H6. This is also C3H6, which is why the cycloalkanes can sometimes behave like alkenes. Right? Cyclopropane can kind of behave sometimes like propene because of that. Yep. All right, so reactions with alkanes. Because the carbon-carbon and carbon-hydrogen bonds are mostly nonpolar, not very reactive. Exception is combustion. All right, so basically you get hydrocarbon, whatever it is, and oxygen, and it's burning, it's combusting to give you carbon dioxide and water vapor. You can also get substitution. Basically, a hydrogen is substituted with a different group. So if you had a carbon chain, and you got all those hydrogens off of it, it's saying, hey, let's take that hydrogen and swap it out for something else. So whatever it is. So here's an example. I got methane reacting with chlorine, and it's giving me chloromethane, right? So I replaced one of those hydrogens with a chlorine, and where did the hydrogen go? It's with the other chlorine that was in Cl2. Okay? So tell me, what can you say about alkanes and their properties? What can you say about structural isomers? What can you say about cycloalkanes? And what can you say about reactions involving alkanes and alkane reactivity? Okay? I hope you found that helpful. I'll see you in class. Bring questions. Okay, bye.